Okay, Assalamualaikum warahmatullahi wabarakatuh. Very good evening to everyone. Can you all hear me loud and clear?
Yes, Dr. Loud and clear.
Okay, thank you very much. Okay, let's move on to today's lecture. Okay, just before that, towards the end of this lecture, I will definitely inform you about our exam and also some other few things that I wanted to do well this week after today's session with you all. So let's move on with the lecture first. So in the meantime, let me just put up the slide. Okay, can you see my slide?
Yes, Doctor.
Yes, Doctor.
All right, okay, let's start. Okay, today will be our last lecture. Today will be our last chapter for the title of engine heat transfer. Okay, engine heat transfer is among the chapter that will be coming up for exam. So pay attention closely. Give me.
Sorry, sir. The sound suddenly turned too low.
Sorry, can you speak louder? I cannot hear you. Sorry, can you repeat the question?
Okay, so I think it's my problem. My phone like a bit problem, but now okay already. Sorry,
Okay.
sorry.
All right. Okay. Okay. Yes, engine heat transfer will be definitely coming out in your exam. It's among well, in your exam basically there's four main chapters that will be focusing on, and engine heat transfer is one of the chapters in your exam. Okay, so don't worry so much. Because I will definitely provide you some exercises and solution this week for you all to practice up until your exam. Okay, so don't worry. So engine heat transfer is broken down into three sub-chapters. The first one is engine cooling system. Second one is engine heat transfer itself, and sub-chapter 3 would be engine operations. So under this engine cooling system, we're gonna basically fundamentally understand what is cooling system, okay, the components, the system itself, before we go into heat transfer. So what is actually a cooling system? Okay. So so just imagine if you just imagine if you have a typical four-cylinder engine, okay, in a vehicle cruising along a highway at around 50 miles per hour. So during this operation, the engine basically will roughly produce about 4,000 explosions per minute. Okay, and this will definitely, because the fact that there's so many explosions, okay, will definitely produce an enormous amount of heat. Okay, there's so much heat will be produced. Okay, and of course, if not controlled, this heat will destroy your engine in matter of minutes and so forth. Okay, so controlling these high temperatures is basically the main job for the cooling system. Okay. So today's cooling system must maintain the engine at constant temperature, whether the outside air temperature is 45 degrees or even worse in Malaysia, or in some of the hot climate countries, especially in the Middle East countries and so forth. Air temperatures in Middle East countries can go up to between 70 to 90 degrees. But surprisingly, in Malaysia itself, if you are driving in congested traffic, this is actually based on some experiments that we did. Air temperatures inside the engine that goes into the air intake system might reach up to 60 to 70 degrees Celsius, okay, 60 to 70 degrees Celsius in congested traffic in Malaysia. So if the engine temperature is too low, then this is also not good. It will definitely affect the fuel economy, and the emission, of course, will increase. If the temperature is allowed to get too hot for too long, then it will destroy or damage the engine components and so forth. So, it cannot be too hot and it cannot be too cold, okay, guys? So if you look through some of the main components in a typical cooling system of a normal passenger car nowadays, it's basically consists of radiator, pressure cap, thermostat, fan, water pump, and of course hoses. So how does a cooling system work? Basically, it sends the coolant through passages in the engine block and also cylinder head. Most importantly, it has to go through the cylinder head, because cylinder head has the highest temperature compared to the other components, okay? So as the coolant flows through these passages, okay, it absorbs the heat from the components, from the surface of the components. The heated fluid then makes its way through rubber hoses to the radiator in the front of the car. This is where the heat is being exchanged by the air that flows through the radiator fins. So as it flows through the thin tubes in the radiator, or what we call as fins, the hot liquid is cooled by the airstream entering the engine compartment from the front grille of the car. So once the fluid is cool, it returns, or basically, not to say cool, if once the fluid temperature is brought down, then the fluid will then return to the engine to absorb more heat. So it's a cyclic event. The water pump has the job of keeping the fluid moving through this system of plumbing and also hidden passages. So without water pump, there's a high possibility that the water will be static. It will not flow throughout the engine. Now, radiator is among the main component of a cooling system. Okay, the radiator core is usually made of flattened aluminium tubes with aluminium strips that zigzag between the tubes. So these fins transfers the heat in the tubes into the airstream to be carried away from the vehicle. On each end of the radiator core, there's a tank, usually made of plastic, that covers the ends of the radiator. So you can look at the picture in the following slide. On most modern radiators, the tubes run horizontally with the plastic tank on either side. So the water that flows in the radiator is actually moving horizontally, okay, not vertically. On other cars, the tube runs vertically with the tank on the top and bottom. So some cars, seldom, okay, I would say nowadays the trend has becoming more likely to be horizontal than vertical nowadays. On older vehicles, the core was actually made of copper and the tanks were brass. Okay, this is the older. This is, well, you look at 10 to 15 years ago. Why they changed to plastic is because of the cost reduction, but definitely copper and brass has a better efficiency compared to plastics, because they actually it basically brings down the temperature at a much faster rate compared to plastics. So the picture over here is the horizontal ones, because you have the plastic covers on the left and right side of the radiator core. So the tanks where the plastic or brass each have a large hose connection, one mounted towards the top radiator to let the coolant in, the other mounted at the bottom of the radiator on the other tank to let the coolant back out. So the entry would definitely needs to be from the top. And of course, on the top of the radiator is an additional opening that is capped off by the radiator cap. Okay, if you look to any particular, if you look to any modern engine nowadays, you can actually notice that the radiator cap is positioned at the highest point of the engine. Okay, you can actually note that because the fact that the pressure cap function is supposed to regulate the pressure inside the cooling system. So as coolant gets hot, it expands. Okay, so since the cooling system is sealed, this expansion causes an increase in pressure in the cooling system, which is normal and actually part of the design. So that's normal. So when coolant is under pressure, temperature where the liquid begins to boil is considerably higher. So this pressure, coupled with the higher boiling point of ethylene glycol, allows the coolant to safely reach the temperature in excess of 120 degrees Celsius, provided that you are using the correct antifreeze and also the correct ratio between water and antifreeze. Otherwise, you cannot get the boiling point up to 120 degrees. So that's normal. If you are using normal water, definitely normal waters will usually under pressure. The boiling temperature will probably reach 105 degrees more or less. But with the assistance of antifreeze, definitely you are raising up the boiling temperature to 120 degrees. So the radiator pressure cap is actually a simple device which you can actually buy. Probably the cost of between 20 to 30 ringgit actually. But it is very important to make sure that the pressure in the cooling system is at its desired value. Okay, if you use incorrect pressure caps, definitely the pressure will definitely be incorrect for that system, and it will actually affect the cooling efficiency of the vehicle. If the pressure builds up higher than the set pressure point, then there is a spring-loaded valve calibrated to the correct pressure value to release the pressure and also to release excessive coolant into a reservoir, into a reserve tank. Okay. So when the cooling system pressure reaches the point where the cap needs to be released, this excess pressure, a small amount of coolant is bleed off. Okay, that's normal. So just make sure that your pressure caps are always the correct specification. If it's meant to control your cooling pressure at 2 bar, then if you replace your pressure cap, it needs to be 2 bar. It cannot be lower, and also it cannot be higher. Okay. It could happen during stop and go traffic on extremely hot day, or if the cooling system is malfunctioning. If it does release pressure under these conditions, there is a system in place to capture the released coolant and store it in a plastic tank. Okay, so this is basically a typical reserve tank, expansion tank. Okay. And this is actually not pressurized, it is at atmospheric pressure. Since there is no less coolant in the system, as the engine cools down, a partial vacuum is formed. Okay, so also there's also a need for you to actually fill in your expansion or reserve tank at certain value, because otherwise you don't want to actually overfill the reserve tank, okay, or nor you don't want to underfill the reserve tank. Okay, there's a reason why. Okay, of course, another important component under the cooling system is the water pump. Okay, a water pump is usually mounted on the front of the engine and turns whenever the engine is running. This is basically mechanically connected to the crankshaft rotation. So the water pump is driven by the engine through a fan belt, okay, or these days can be mechanical gears that will also be responsible for driving an additional component like an alternator, power steering pump, and so forth. The water pump is actually made of a housing and impeller, a spinning shaft, and a pulley attached to the shaft on the outside of the pump body. So this is basically a typical mechanism in a water pump. A seal keeps fluid from leaking out of the pump housing past the spinning shaft. Okay, a seal. This seal is a common problem for water pumps. Okay, usually after certain mileage, if you notice that some of the coolant being leaked at the water pump, this is probably due to a failed seal. The impeller uses a centrifugal force to draw the coolant in from the lower radiator hose and send it under pressure into the engine block. There is a gasket to seal the water pump to the engine block and prevent the flowing coolant from leaking out from the out where the pump is attached to the block. Okay, so the ones that are in these slides are actually mechanical pump, which is connected to the engine rotation either through fan belt or mechanical gears or chain and so forth. But the latest ones are actually electric pump. Okay, I think most of the BMW engines nowadays, the latest ones are running on electric water pump. Thermostat is actually another important function in a cooling system. It is simply a valve that measures the temperature of the coolant. If it's hot enough, it opens to allow the coolant to flow through the radiator so that the heat in the coolant can escape from the engine. Okay, but if the coolant is not hot enough, the flow to the radiator is blocked, or in other words, the valve is closed lah, and fluid is redirected to a bypass system that allows the coolant to return directly back to the engine and to continue to collect the heat from the engine. So the bypass system allows the coolant to keep moving through the engine to balance the temperature and avoid hot spots. Okay. So the bypass is really very, very important to make sure that the heat is evenly distributed throughout the engine. And bypass, because flow to the radiator is blocked, the engine will reach operating temperature sooner, and on a cold day will allow the heater to begin supplying hot air to the interior more quickly. Okay. So in other words, thermostat is it's a clever invention. It blocks the coolant flow exiting the engine, because the fact that it wants the engine to raise the temperature as quickly as possible, and also allows the coolant to exit the engine for the coolant to actually remove the heat. Okay. The heart of the thermostat is a sealed copper cup that contains wax and a metal pellet. Okay, so inside the thermostat there's a wax and a metal pellet, so it expands and contracts according to temperature. So as the thermostat heats up, the hot wax expands, pushing a piston against spring pressure to open the valve, hence closing or blocking the water flow. Okay, and allow coolant to circulate by opening the valve. Okay, so but again, nowadays with the latest inventions so far, they do longer well, I would say most, I would say minority has started to use electric thermostat nowadays. So instead of using this wax and metal pellet, they have been using solenoid or electronic valve as a replacement for this thermostat. Okay, especially on, you can see that on the latest Ford cars, I think most of the latest Ford cars are actually have been using electronic thermostat. Hoses, yes, there are, well, basically it's quite straightforward. There are several rubber hoses that make up the plumbing to connect the components of the cooling system. Okay, production hoses are actually quite cheap. Okay, and which is why the quality is not as good the ones that you can buy in the aftermarket. So the main hoses are called upper and lower radiator hose. These two hoses are approximately 2 inches in diameter, roughly. It may vary from 1.8 to 2.2 inches depending on the size of the engine, and directs the coolant between the engine and also radiator. It connects the connection of the coolant flow. So 2 additional hoses called heater hose supply hot coolant from the engine to the heater core. So this is basically a typical connection or additional system which they call as heater system. These are actually for cars that is actually market in cold climate countries lah. Okay. So these hoses are approximately 1 inch in diameter. One of these hoses may have a heater control valve mounted in line to block the hot coolant from entering the heater core when the air conditioner is set to maximum cool. Okay. In the case for Malaysian market, because the fact that we only have one climate, okay. So and one climate is always hot in Malaysia, so therefore there's no necessity in Malaysia or some of the, and also Middle East countries, okay, and probably some of the countries that has one climate, there's no necessity for them to have a heater system, okay, which is why some of if you buy imported cars from the US and Europe and some of the cold climate countries or seasonal countries, these cars are actually equipped with a heater system. Antifreeze, okay, antifreeze is very important. The coolant antifreeze is the coolant that circulates through the engine and associated with plumbing. Must be able to withstand temperatures well below zero without freezing, okay. It must also be able to handle engine temperature in excess of 120 degrees Celsius without boiling, okay. The fluid must also contain rust inhibitors and a lubricant agent, okay. This is the 3 main criteria, important criteria in antifreeze, okay. Coolant in today's vehicle is a mixture of ethylene glycol, or what we call as antifreeze, and also water. It's a mixture. The recommended ratio is always 50-50. In other words, 1 part of antifreeze and 1 part of water. This is the minimum recommended for use in automobile engines, but the ratio between antifreeze and water might vary between vehicles and manufacturers. So always refer to the manufacturers or manual vehicle manual book. Okay, less antifreeze and the boiling point would also be too low. In certain climates where the temperatures can go well below zero, it is permissible to have as much as 75 degrees antifreeze and 25% water, but nothing more than that. Okay, so 75 to 25 is the highest ratio recommended. So pure antifreeze will also not work properly and can also cause boil over. So if you have so much money, no need to buy so much antifreeze and put all the antifreeze inside your car, because that will not work. Okay, that will definitely not work. Okay, so okay, that's pretty much just a fundamental of about roughly about cooling system. Are you all okay? Is there any question you want to ask before we move on to heat transfer in engine?
Question, Doctor.
Okay, good.
Doctor, one
Yep.
question about coolant, sorry. For is the coolant that we use in Malaysia, there's a myth said that the different colors means different contents of the cooler. The contents too in terms of what? Because is it in terms of the antifreeze mixture or something like that?
Okay. Yes, I think well, yes, there are some truth about of what you say about the colors. Yes, colors are so okay. This is the scenario because the fact that some manufacturers, they have agreed between themselves to produce certain colors for certain specification. While some other manufacturers, they don't really care. Okay, and because the fact that the antifreeze specification or standard or world standard does not specify the color. So if you follow to the API or ASTM specifications to under the control of antifreeze for passenger car, the regulations does not state that the color plays as an indicator to specify the specification. But just between some of the manufacturers, they have mutually agreed, okay, let's produce certain colors for these specifications and so forth. So it's not a reliable statement, but well, the fact that some manufacturers, they prefer their antifreeze to be red. Some manufacturers, they prefer their antifreeze to be green. There's a reason why they choose red and green, because the fact that there's another purpose of antifreeze actually, is actually for if there's any leakage, okay, if there's any leakage, you can clearly see the leakage because of the distinct colors. And the fact that some of these colors are actually the choice of colors need to be carefully selected because the fact that they don't want to confuse that with the other types of fluid used in engines such as grease, other types of lubricant and so forth. Which is why some manufacturers, they prefer the coolant to be green or red. And which is why some manufacturers they have some certain understandings and they have some certain collaborations in certain engine developments and so forth, which is why some manufacturers, they agreed to, like, let's go for red. For example, Toyota is always been producing coolant with red color, and also Daihatsu same as well, I think, because the fact that they are under the same umbrella. But in terms of legislations or fluid control standards, such as from API or ASTM, there's no regulation stating that there's no regulation that states the color is part of the specification. Does that answer your question, Daniel?
So that means that even we have all these different colors coolant, there are no difference between their composition.
Yes or no? Yes and no. Because the fact that it's not being standardized throughout manufacturers. Only certain manufacturers, they agree, they volunteered to go for certain colors distinction.
So that means there are no really proper standard in terms of coolant.
Yeah, correct. Because
I see.
because the standard that is being controlled only covers the content and also the capability of the coolant. But it doesn't specify it needs to be green. It has to be fluorescent green or
Okay.
you get what I mean?
Yeah. Okay, thank you, Doctor.
Okay. Let's move on to subchapter number 2, which is heat transfer engine. Okay, this is basically the what. So now you know basically have an understanding of the cooling system. Let's move on to the heat transfer in engine. Okay. So about 35% of the total chemical energy that enters the engine is converted to useful crankshaft work. So if you have, let's say that if you have 10 liters of fuel, okay, 10 liters of fuel being pumped into the engine, okay, only 3.5 liter is being used to into useful work. Okay, only 35%. Whereas 30% of the fuel energy is carried away, wasted just like that in exhaust flow. Wasted just like that in exhaust flow. Hence come the turbocharger, which is turbocharger is supposed to basically make use of this 30%. Okay. And then this leaves about 1/3 of the total energy that must be dissipated to the surroundings by some mode of heat transfer. Okay. So therefore, engine cooling is very, very important to prevent excessive heat buildup and thus avoid material damage and engine failure. So this is basically, I guess, probably by now you should all, I think most of you should already be aware of the, you should be able to recognize these components in your vehicle, radiator, fan, water pump, lower hose, top hose. Thermostat, it's hard to see because it's usually covered and being located inside a housing, so you cannot see a thermostat. Pressure cap, yes, you can clearly see pressure caps in front of the on top of the radiator. Reserve tanks or expansion tanks on the car. Heater core, heater hoses. This is usually heater core is usually positioned inside the cabin, but mostly for vehicles that is marketed in cold weather. Yeah. So in other words, there are generally two methods of engine cooling. Of course, the one that we have covered just now is the water cool. Okay, cylinder block water jacket is filled with coolant or antifreeze, circulated throughout the engine by the water pump. And another one, which is the air cool, which is typical in old cars and also some mopeds. Okay. So engine is actually for air cool system, engine is actually designed with fins, okay, to increase the heat transfer surface area over which airflow is directed. So if you see an air cool engine, you can actually distinguish by the design of the fins on the cylinder head and also cylinder block. So energy distribution the amount of energy or power available for use in engine can be calculated by the fuel flow rate into the engine times the heating value of the fuel. Okay, so mass flow of the fuel is limited by the mass flow of air. So these statements tell you that the amount of fuel is depend on how much air that goes into the engine. Okay, it's not the other way around. Okay, how much fuel needs to go, how much fuel needs to be injected, well, that depends on how much air you can squeeze into the engine. More air, and of course you can put in more fuel to get more power. Okay, otherwise don't dream about giving more fuel. Okay, so brake thermal efficiency gives the percentage of this total energy that is converted to useful output at the crankshaft. Okay, so the brake thermal efficiency can be calculated by the brake power divided by the fuel fuel flow times the heating value and times the thermal efficiency of the engine. Now this graph is very, very important. The rest of energy can be divided into heat losses, parasitic loads, energy loss in exhaust flow and so forth. So this is basically a typical distribution of energy in internal combustion engine given as a percentage of the total fuel energy. So just imagine if you have a certain amount of energy at 100% is being provided into internal combustion engine. You can see that the 20 to 30% is effectively being used to produce brake power, but the rest is just all wasted. Okay, you can see that probably 40% is being used in coolant load, 20% is being used in the exhaust, 10% is being used in friction, and also heat losses to the surroundings. So just make sure you understand this graph, because I will tell you definitely this will definitely coming out in your exam. So for any engine, power generated, okay, is basically a sum of the total work produced in the crankshaft, energy loss in the exhaust flow, and also losses to the surrounding, and also not to forget about the ancillaries. Okay, ancillaries, this should definitely is the power that is being wasted to other components such as your alternator, your starter motor, your electrical loading, and so forth. Okay, so etc. etc. So by then, a typical range for power that is being transferred to the crankshaft, you can say, is probably between 25 to 40%. And until today, we hardly reach above 55%. We hardly reach 50%. CI engines, compression ignition engines, are generally on the high end, whereas spark ignition engines are on the lower end of this percentage. Okay. So energy loss in exhaust flow is roughly about 20 to 45%. Okay, 25%. This actually, these values, the range of percentage is referring to this graph. Okay. So greater percentage of energy loss is lost in the exhaust of spark ignition engines because of their higher exhaust temperature. Okay, so lost exhaust energy is made of two parts, which is the enthalpy or heat, and also chemical energy. So when engine run at rich mixture at wide open throttle, so chemical energy makes up about half of the exhaust loss. So under many operating conditions, lost exhaust energy exceeds the brake power output of the engine. So this is just for your information lah, on what's going on with the exhaust loss. Other losses to the surroundings can range between 10 to 35% depending on the engine design itself. But for many engines, the heat losses can be divided into coolant, oil, and also ambient. Okay, so these three are the main ones, but of course it can go to other areas such as power steering fluid, transmission fluid, and so forth. Okay, so with compression engines on the high end, heat flow to the coolant is roughly about 10 to 30%. So on CI engines, the heat flow to the coolant is slightly lower compared to the spark ignition engines. At high load, energy loss to the coolant can amount to about half of the brake power output, because the fact that when you produce so much power, there's so much heat and there's so much energy is being produced that the temperature increases significantly. Okay, increasing to about twice the brake output at low load. Okay, depending on the type of oil and engine speed, losses, heat losses on the oils, this one inclusive of the engine oil, transmission oil, and so forth, can vary between 5 to 15%. Okay, this is just some guidance for you. You no need to remember this one. Losses directly to the surroundings, such as ambient. Okay, this is actually heat that is being dissipated to your front bonnet, to your cabin, and so forth. So whenever the heat is being dissipated to the environment, that is roughly between 2 to 10%. Whereas on friction losses, actually we could definitely cover to up to 10%. So if you look into the breakdown on the temperature mapping in a combustion chamber, you can see that cylinder head has the highest temperature. It may reach to between 600 to 1000 degree. So typical temperature values in spark ignition engines operating at a normal steady state conditions lah. So three of the hottest points around the spark plugs, the exhaust valve and ports, and also the face of the piston. Okay, these points locations are also difficult to cool. Okay, which is why I think in the latest or modern internal combustion engines, you can see that the design of the cylinder head are very complex, whereby they have a very quite complicated coolant passage, okay, just for the purpose of extracting or cooling down the cylinder head temperatures, okay, especially around the combustion chamber. Engine warm-ups, okay. Engine warm-up is basically some of the conditions that usually being strategized in modern vehicle nowadays. So as a cool engine heats up to a steady state temperature, the thermal expansion occurs in all components. So this only happens during when you, if you usually happen in the morning lah, yeah. So magnitude of the expansion will be different for each component, okay, but depending on its temperature and the type of material. Of course, the most fastest to warm up is around the combustion chamber, okay, specifically the spark plug and also exhaust valve. These two components are the ones that will reach its a normal operating temperature first before other components. In cool weather, the startup time to reach steady state can be as high as 20 to 30 minutes. Okay, if you want to wait during idling, if you can just imagine if you start your engine in the morning, it will, for you to get the engine components to reach its normal temperature, it will take between 20 to 30 minutes. Okay, so some parts of the automobile reach steady state much sooner than this, but some do not. Okay, but in the case of 20 to 30 minutes, this is when usually all the components has reached to a normal temperature. If you are idling, but I don't think most of us can wait the 20 to 30 minutes in the morning just to do nothing lah. Okay, so fairly normal operating temperatures may be experienced within a few minutes, but it can take as long as an hour to reach optimum fuel consumption rates. Okay, engines are built to operate best at steady state conditions. Full power and optimum fuel economy may not be realized until this state is reached. You can never achieve a full power or optimum fuel economy unless your temperature of your components reach to its desired temperature or its operating temperature. A large percentage of automobiles run for short trips with engines that are not fully warm up. This contributes to the major cause of air pollution, of course. Okay, when the engine components or the engine itself haven't reached its normal or desired working temperature, it will definitely consumes more fuel. Hence, you emit more pollution. Heat transfer in intake system. So as the air fuel mixture enters engine through the intake system, its temperature increases from ambient condition to about 60 degrees. Okay, roughly. This is just a estimation. This is due to a number of thermodynamic processes to which the intake air is subjected. The wall of the intake manifold are actually hotter than the flowing gas. Okay, heating them by convection. So this is basically how you can actually estimate of how much energy or heat by subtracting the temperature difference and also the convection heat transfer coefficient and also the surface area of the intake manifold. Okay, so the manifold is hot, the location is close to other hot components in the engine compartment and so on. I won't go through this carburetor because it's a old technology and we're definitely not coming out into your exam, so I'll skip this one. So there are several consequences from convective heating in the intake manifold. Some are good, some are bad. So the earlier the fuel get vaporized, the longer it is mixed with air. Okay, so you want to as soon as the fuel is being injected, okay, you want the mixture to immediately happen so that you have a longer mixture by the time this mixture reaches the spark plug for combustion. So therefore, it has a more homogeneous mixture. Increasing intake and temperature will definitely reduce the volumetric efficiency. Okay, but there's and also reduce the air density and reduce mass of air to the cylinder. But you definitely need to have a higher, I wouldn't say higher, a warm intake temperature to vaporize some of the fuel, to assist the vaporization of the fuel with the air in the intake system. So there's pros and cons. Okay, what it meant by to have a slightly warm temperature, so just sufficient enough to assist the vaporization. But if it's too hot, then it will affect the volumetric efficiency. It will reduce the air density and also to reduce mass of air to the cylinder. But in the case of where you have the air temperature too cold, then your air, the vaporization will not be efficient. The reason to limit the heating of the inlet air is to keep temperature to a minimum at the start of compression stroke. The higher the temperature at the start of compression will contribute to engine knocking. Okay, because the fact that because we already discussed this before, and the fact that we know that temperature is among the culprit or the cause for knocking, which is why we don't want to have the air temperature that goes into the combustion chamber too high. So port fuel injection engines have less need for heating the intake manifold. It relies on the finer droplets from the injector system and higher temperature around the intake valves to assure necessary fuel evaporation. So on most of the PFI engines, this is the vaporization of fuel is not so much of concern. Fuel is sprayed directly onto the back of the intake valves, okay, and speed evaporation process and cool the intake valves. So instead, fuel, yes, it's another purpose for fuel is definitely to reduce the temperature, either to reduce the intake valve, and also to reduce the combustion temperature itself. For supercharged and turbocharged engines, the inlet air temperature is also affected by the resulting compressive heating. Thus, aftercooler is introduced to lower the temperature. So, which is why on turbocharged or supercharged engines, forced induction engines, intercoolers or aftercoolers, okay, what we call it intercoolers nowadays. Those days we call it aftercooler. Intercoolers are actually necessary for forced induction engines because the fact that they want to bring the temperature down. Okay. Once the air fuel mixture in the cylinder is in the cylinder, all three modes of the heat transfer, conduction, convection, and radiation plays important part for smooth steady state operation. Air fuel mixture that enters the cylinder during intake stroke may be hotter or cooler than the cylinder wall, heat transfer being possible in either direction, vice versa. Okay. About 3000 Kelvin of peak gas temperature is recorded during the combustion. Effective heat transfer is needed to keep cylinder walls from overheating. Okay. Convection and conduction are the main heat transfer modes to remove energy from the combustion chamber and keep the cylinder walls from melting. Okay. This is basically a diagram of heat transfer through the cylinder wall, combustion chamber, wall of internal combustion engine. So there's a clear difference. On the left is the coolant system. Okay, so you can see that how the heat transfer is being distributed between the combustion chamber through the cylinder wall and into the coolant, whereas on an air-cooled engine, from the combustion chamber through the cylinder wall, through the fins and into the airstream that passes through the engine. So cylinder gas temperature and its convection heat transfer coefficient are vary over large range for each engine cycle. Coolant temperature and its heat transfer coefficient are fairly constant. Thus, heat conduction is cyclic for a small depth into the cylinder wall on the combustion chamber side. Heat transfer in combustion chamber, heat transfer per unit surface area will be, you can use this equation to actually calculate the heat transfer per unit surface area. Okay, this one you can go through by yourself. And also convection heat transfer on the inside surface of the cylinder. Okay, this is the inside of the cylinder. You can use this equation, and also a tip. This is how you can actually. There are a number of ways of identifying Reynolds number to use for comparing flow characteristics and heat transfer engines of different sizes, speeds, and geometries. In the case of where you are required to calculate, okay, the Reynolds number, you can use this formula. Okay. So from this Reynolds number, okay, a Nusselt number can be calculated, okay, for the inside of the combustion chamber, okay. So the Nusselt number and convection heat transfer coefficient on the coolant side of the cylinder wall can be approximated by conventional methods of forced convection heat transfer. So heat transfer, you can see that this is basically a plot of the cycle to cycle variation in combustion chamber that occurs within a cylinder result in a cycle to cycle variation in cylinder wall temperature and cylinder wall heat flux. In other words, this diagram basically wants to describe that the heat transfer and also the cylinder wall temperature varies from cycle to cycle. So you can see that there's the variations is quite large. Okay. So it's pretty much and in certain good engines design, in certain good engines, the variations between cycles are at minimum, but on a not in a typical passenger car nowadays, I think these variations is among the issues of why engines are not behaving or not being achieving certain efficiency. Okay, it's just information lah. So aluminum pistons generally operates between 30 to 80 degrees cooler than the cast iron pistons due to the high thermal conductivity. Of course, the usage of better materials can definitely bring down the temperature, but of course you don't want to go for aluminum pistons because it's very expensive compared to the cast iron. And of course, by using aluminum pistons, with the fact that you can actually reduce the thermal conductivity, you can actually also assist to reduce knocking problems, but also can cause greater thermal expansion problems between dissimilar materials, especially between if you have aluminum pistons, but you have cast iron as in the wall. Okay, so many modern pistons have a ceramic phase and operate at a high steady state temperature. Okay, this is usually most of the pistons on internal combustion engines are actually coated with ceramic. Ceramic has a poor heat conduction properties but can tolerate much higher temperature. So some very large engines have a water-cooled pistons. I hardly see this nowadays. I think what I can see that most of the piston nowadays are actually coated with ceramic. Okay, to avoid thermal breakdown of the lubricating oil, it is necessary to keep the cylinder wall temperature from exceeding 180 degrees to 200 degrees. As lubrication technology improves the quality of oils, this maximum allowable wall temperature is being raised and so forth. Another important thing also, the engine oil also plays a role to cool down the combustion chamber besides the material itself. So that's pretty much on engine heat transfer. Is there any questions? Okay, good. There's no questions. Don't worry so much on engine heat transfer, because I will provide you some exercises and solution for you all to practice this week, but not today, in a few days time. then only when you go through the exercises, also always refer to the notes so that you have some explanation on top of the as a fundamental or understanding when you go through the exercises. Okay, let's take a 10 minutes break before we continue to the last chapter, which is the chapter 10.3. Is that okay if we go for 10 minutes break?
Yes, Doctor.
All right, I'll see you back in now my time is 9 sharp at 9, so we'll continue back at 9:10. See you back then. Okay, let's continue this. Finish this one. Hopefully, we'll probably finish by 9:30 or something. Can you all hear me? See my slide?
Yes, yes.
Okay, moving on into engine operation. Okay, we're gonna cover some of the operations of an engine. Okay, so effect on engine operating variables on heat transfer or heat transfer within engines depends on so many different variables that is difficult to correlate one engine with another. So it depends on the engine operation to distinguish its heat transfer. Okay, so these variables includes air fuel ratio, speed, load, brake mean effective pressure, spark timing, compression ratio, materials and size, and the fact that these variables are actually different from one engine to another. You can't actually directly compare, even though the engine has a same size, such as between 1.6 liter engines, even in between 1.6 liter engines, because the fact that they operate the variables varies during the operation. So therefore, the heat transfer between the engine in the same category might also vary. First of all, the engine size. So if two geometrically similar engines of different size, displacement, are run at the same speed, and all other variables such as the temperature, air fuel ratio, fuel, spark timing, etc., are kept as close to the same as possible. So the larger engine will have a greater absolute heat loss, but will be more thermal efficient. So this is just a rule of thumb. So if the temperature and materials of both engines are the same, heat loss fluxes to the surroundings per unit area will be about the same, roughly about the same. So, but the absolute heat loss of the larger engine will be greater due to the fact that the components has a larger surface areas. Engine speed. As speed increases, so gas flow velocity into and outside the and exiting the engine will increase. This increases the turbulence and convection heat transfer coefficient inside the engine. Time of the cycle is less at high speed, so because the fact that the rotational speed is much more greater, less heat transfer per cycle occurs. So this gives the engine a higher thermal efficiency at higher speed. Okay. At higher speeds, more cycles per unit time occurs, but each cycle lasts less time. Okay. And the net results is a slight rise in heat transfer loss with time from the engine. This is partly due to the higher heat losses for part of the cycle, but mostly due to the high steady state losses which the engine established at high speed. So you can see that as the engine speed increases, most of the heat produced is increases, but you can see that exhaust gas and exhaust valve has the highest increase compared to other components. So heat transfer to the engine coolant increase with engine speed. So this one can be measured or calculated using this equation of convection heat transfer coefficient times the surface area and also times the delta T between the coolant temperature and also the wall temperature. Engine load can also be calculated. As load increases, heat transfer within the engine also goes up with the product of convection heat transfer times the surface area at any point and also delta T, okay, temperature difference at that point. So spark timing, more power and higher temperature are generated when the spark setting is set to give a maximum pressure. So in other words, if you have the spark timing in an advanced position, or in order to have the peak combustion pressure at roughly about 5 to 10 degrees after TDC, more higher temperature will be produced. So these higher peak temperatures will create a higher momentary heat losses, but this will occur over a short length of time. So with spark timing set either too early or too late, combustion efficiency and average temperature will be lower if it's too late or too early. So if you can just recap, that the main intention for the spark timing is to have the peak combustion pressure roughly in the range between 5 to 10 degrees after TDC. It cannot be too late, it cannot be too low. Too late or cannot be too advanced. So these lower temperatures will give less peak heat loss, but the heat losses will last over a long length of time, and the overall energy losses will be much way greater. Other variables that affect on heat transfer also include the fuel equivalence ratio. Okay, this is fuel equivalence ratio is basically the vice versa of air fuel ratio, evaporating cooling, inlet air temperature, coolant temperature, engine materials, compression ratio, knock, swirl, and squish. So these are all some of the engine design and also engine parameters that has been set. So that is pretty much very quick one on the engine operations or how it does affect the heat transfer. Is there any question? Okay, good. If there's no question, regarding this chapter, I will pass to you the exercises. Okay, not just for this chapter. I will pass you exercises for actually for 3 chapters. One is for combustion. Second is exhaust. Okay. Third one is heat transfer. So there will be 3 chapters. So these exercises will actually also prepare you for your exam as well. Okay, so for your exam, you definitely need to basically do some practices based on the 2 exercises that I will give you. The first one is basically the one that I gave you a couple of weeks ago. The second one will be sometime this week. Okay, hopefully I'm planning to distribute exercise 2 by Wednesday. So if you ask me common questions, what will be coming out in your exam? I will give you about there's 4 chapters that will be coming out definitely. Combustion, exhaust, heat transfer, and the last chapter would be let me check my notes. Energy distribution. Okay, energy distribution. So that will be, so your exam will be on the 3rd of July. That will be on Saturday. Yeah, there will be 4 questions. There will be 4 questions. There will be 4 questions. 2 of the question will be given. The exam is split into 2 parts. The first part, part 1, whereby it consists of 2 questions, will be given to you to do at 10 a.m. in the morning. Okay, and you'll have 1.5 hour, to complete those 2 questions, and then you need to submit part 1, and then later at 2 p.m. we will start part 2, where you will be given another 2 more questions for you to do in 1.5 hour. So in total you have 3 hours, but each part is 1.5 hour. Any question on exam?
What's the last chapter yang Dr. said just now?
Energy distribution. Any questions so far? Okay, good.
So 4 chapters are inside the test.
Yeah.
Is it answer all question or choose one question?
Yes. Answer all question.
Okay.
So remember, let me just repeat back. Your exam will be on 3rd July, Saturday. Your exam will be split into part 1 and also part 2. Part 1 will start at 10 a.m. You will have 1.5 hours to complete 2 questions and submit. And then part 2 will start at 2 p.m. You will be given another 2 more questions for you to complete within 1.5 hour. So each part is 1.5 hour. And of course, you need to submit each part according to the time lah. You cannot submit part 1 during part 2. Okay? So chapters, you will be concentrating on combustion, exhaust blowdown, and heat transfer. And of course, energy distribution. But let me tell you also, in some of the questions, combustion, exhaust, heat transfer, and energy distribution, it may require you some understanding and also your capability for you to use other chapters as well. So if you want to do revision, yes, please do exercise 1 and please do exercise 2. Exercise 1 is basically the exercise that I already gave you a few weeks ago. Exercise 2 will be given to you this Wednesday or Thursday, inshallah. Yes, it will be an open book exam. Okay, you can refer to any books. Okay, but and so forth. But you cannot discuss or copy from other people. It's the same thing as what we did during the test. Okay, any questions so far, Maggie?
And also, when are we going to get our carry marks? Okay, will we get it before the finals or?
Yeah, definitely before the finals.
All right, okay.
Yeah. I'm still at the moment, yeah, definitely. Just before the finals, I will give you all the carry marks. Okay, other than that, today will be your deadline assignment, assignment 2. So please make sure for those who haven't submit, you have until 12 a.m. tonight for you to submit. For those who already submitted, thank you very much. The next thing, for those who already submitted, the next thing for you to do is just to prepare for your exam. Okay, so from today up until Wednesday or Thursday, if you want to start, probably you can start practicing on exercise 1 first. Okay. Okay, everyone. Today is our last session. Thank you very much for paying attention and also participating in the class. Thank you for your attendance. Other than that, just before I leave, kalau ada salah dan silap terkasar bahasa, saya nak mohon maaf. Kalau ada terkasar bahasa ke apa, saya hanyalah manusia yang biasa. Okay. Other than that, keep in touch. I wish you all the best. If you have any questions regarding exercise, please do contact me. I'm happy to assist you. Before the exam. During the exam, I cannot do anything. Other than that, good luck also on your other subjects as well. I wish you all the best. Other than that, thank you very much, everyone. Assalamualaikum warahmatullahi wabarakatuh.
Thanks to you, Doctor. Assalamualaikum.
Thank you, Doctor.
Thank you, Doctor. Waalaikumsalam.
Okay, doctor.
Terima kasih, Doktor. Thank you, Doktor.
Thank you.